For our next speaker. First, I want to thank Pros for sponsoring this session, How to Teach AI Multiple Languages. Again, please, if you have any questions, put them in a chat box. We'll get to it at the end. I'm very happy to introduce our speaker, Rama Akkiraju, IBM Fellow, Master Inventor, IBM Academy member at IBM's Automation Division, where she is also the CTO of AI Operations. And AI Operations is all about optimizing information technology operations management using AI. Thank you, Rama, for being here.
Thank you, Angela. Can you hear me okay?
Yes.
Great. Let me start sharing my screen and then we'll get going here. Can you see my screen?
Yes.
Yes, I take that as a yes. Okay, I'll put it in screen share in just a bit, but good morning, good afternoon, good evening, folks. It's a pleasure to be here. Thanks to Rice University for having me here. I wanted to talk about what it takes to teach AI multiple languages. Such an interesting problem. We all, if we were in a face-to-face room, I would have asked you all, how many of you speak more than 3 or 4 languages? We all know understanding human language is in itself pretty complex. Now add to that making AI understand the language of the enterprise in order for it to be useful and to teach it multiple languages. So when I talk about multiple languages in this talk, I'm talking about AI being able to speak not only the multiple languages that humans speak, but also the languages of companies. So just to kind of get ourselves going here and motivated, I wanted to play these 2 1-minute commercials from Xerox. One is from several years ago, 1977, and the other one somewhat more recent. Let's take a quick look and then we'll get back to the presentation.
Ever since people started recording information, there's been a need to duplicate it.
Very nice work, Brother Dominic. Thank you. Very nice. Now, I would like 500 more sets.
Brother Dominic, how are you?
Could you do a big job for me?
The Xerox 9200 duplicating system, unlike anything we've ever made, feeds and cycles originals, has a computerized programmer that controls the entire system, can duplicate, reduce, and assemble a virtually limitless number of complete sets, and does it all at an incredible 2 pages per second.
Here are your sets, Father. The 500 sets you asked for. It's a miracle.
Okay, that was in 1977. Let's take a look at the current ask.
Brother Dominic, sir. Nice work, Brother Dominic. Very nice.
Thank you.
Now we just need 500 more, translated into 35 languages, personalized for every brother and sister, and shared across the 7 continents. Now, where were we?
Qué bonito. Ay, está lindo.
Yeah, Dominic, ma. Mọi người sao? Chúng ta là Dominic first.
Ah, magnificent.
Quiero besar.
Brother Dominic again.
Look, Abbott, I got it.
It's a miracle.
All right. So yes, businesses, including religious organizations, I suppose, want to reach out to their customers in multiple languages. And as we increasingly use AI as part of business processes and applications, we need AI to be speaking multiple languages. I wish it's a miracle and I wish it's magical that we can just simply teach AI multiple languages like the commercial that we had seen. But even in that commercial, actually, there was nothing magical about it. There was a lot of hard work, and that was a combination of mechanical and digital systems. Same goes here. To teach AI to speak multiple languages, we have to do a lot of hard work behind the scenes. So let's take a quick look at what that hard work is and what it entails to make AI really speak, understand multiple languages. I'll use the word polyglot going forward for somebody who is multilingual, basically a person who knows and is able to use several languages. So for short, I'll start using the term polyglot AI. So here are the key takeaways. I would, in this talk, premise that to build polyglot enterprise AI, we need techniques that address not only the language of the humans, but also the language of the enterprises. So I'll tell you what that means. Second, you don't have to solve the broad AI problem or even solve the understanding of each human language to perfection in order to really get the business use cases going. There is no shame in solving the narrow AI problem as opposed to going for the broad AI. Third, depending on the availability of labeled data, your transparency requirements for the business use cases and explainability requirements, different techniques may have to be applied to build polyglot enterprise AI. I know those three things may sound somewhat abstract at the moment, so let's go through the rest of the talk and I'll illustrate them with more examples. First, let's try to understand the language of the humans. How many languages are in the world? Where it turns out anywhere from 6,500 to 7,000 plus known languages, out of which 23 are the most spoken languages. But businesses typically do their business in companies in 170 plus languages. So when we're talking about the scope and size of the problem, we're talking about this. Most companies start with, probably if they are in multiple parts of the world, different countries, start with 20 plus languages to at least, and then depending on how widespread you are, it may go up to 100 plus languages very quickly. So we are talking about those many languages for teaching AI also to be able to speak. Let's look at the complexity of understanding human language. We all know human language is not exactly as we say it or as we read it. There are a lot of idioms, humor, sarcasm, context, and culture-specific things that are buried inside what we speak, what we write, and that context is very important to understand. If we take any language translation service out there, take any of your favorites, Google, Microsoft, IBM, whatever other companies, and throw in some idioms or sarcastic sentences into it and ask it to translate it to, let's say, another language, see what happens. And here I have tried it actually with the three languages that I speak and understand, English, Hindi, and Telugu. And I've noticed that when I throw in idioms and phrases such as hit a roadblock or selling point, or this other one, the dove, gracefully dove for its seeds, and sort of a sarcastic remark, that's just what I needed today. You can see, for those of you in the audience who understand English and Telugu, can make out that the literal translation falls flat on its face. So yeah, human language is hard. And when I talk about AI speaking multiple languages, I'm talking about the foundational AI services such as language translation, speech recognition, natural language understanding, in which you are trying to understand the sentiments of in the language, the entities, the concepts, and those sort of things, which are then used in various business use cases, such as building chatbots and social media understanding, and so on and so forth. So right there, we can see that there are lots of challenges in understanding one language itself, or doing translation from English to other languages. And we're expecting machines to do as good as humans or better in 170 plus languages. Let's see where we are with regards to technology. As of 2019, if we just look at the leader scoreboards in natural language understanding tasks that are conducted with various latest natural language understanding algorithms on various data sets that are set up on the competition boards, we just look at that, it looks like we are making a lot of progress, and it's actually a defining moment in 2019 when it appears that some of these algorithms and techniques are surpassing humans on some basic natural language understanding tasks. So if the dark black line is what humans understanding of natural language represents, the blue dotted line, which is an average of the various um, on various data sets for each of the techniques, which is the vertical line on the graph that you see that that line starts to surpass human understanding at some point over here. And that makes us start to believe that, okay, maybe we're getting somewhere. We are definitely making progress, but that doesn't mean that we are actually really understanding human language. We, as in that AI systems, are actually really understanding human language. The problem with these data sets is that they use this general language understanding evaluation, GLUE score, on limited classification tasks and specifically restricted to English language only. And they're pre-trained language models. They don't cover many domain-specific terminologies or industry context terms or domains. These are really general understanding of spoken English or maybe written English. And they don't represent real-world tasks. So I would say we are at some level, very simple, small, maybe toy problem level. We're making progress, but we still have long ways to go in understanding human language, just in one language alone. Now, when I talk about multiple languages, I mentioned that I'm not only talking about the human languages, I'm also talking about the language of the enterprise. So let's add that dimension to this problem. So when I say the language of the enterprise, I'm talking about various use cases that are being used in the industry, such as chatbots in customer support, which require intent understanding and speech recognition. And I'm talking about medical healthcare domain AI in it, which includes anomaly detection in radiologies, anomaly detection in cardiograms, and doctor's assistants, note-taking systems, document understanding to summarize, synthesize information, and many other things like that. And in legal domain, I'm talking about understanding the laws, rules, regulations, and extracting them from large volumes of legal text, and also understanding contracts, who owes what to whom, by when, and those sort of things. And I'm talking about use cases in social media where people are talking about their interests, sentiments, their preferences, and those sort of things, and being able to understand that and guide product feedback and product development, and so on. So there are many other use cases in business domains that, in financial services, in public servants domain, in legal, regulatory, in surveillance, in security domain, in facial recognition at airports and such. Many use cases are using AI, and they all have their own individual industry specific languages. Let's take a quick look at that. What do I mean by that? There are two examples, one on the left hand side, one on the right hand side here. But the one on the left hand side is doctor's notes on a patient. So doctor is taking notes with about a patient who is having a specific back pain problem, and what kind of medicine she's taking, in which body part she's having problem, what are her current symptoms and past conditions, and those sort of things. So you can see that there is a lot of vocabulary related to medical domain. On the right hand side is a corporate contract, where there is a lot of specific terminology that relates to who owes what to whom by when, about seller, purchaser, common stock. Now, these are terms that don't naturally occur in general spoken speech all that much. So, if you build a natural language understanding system, whether it is a speech to text transcription system or an entity and recognition system from corporate contracts, just by training those systems with, say, Wikipedia data or other general spoken conversation data, they won't do very well on these domains because they haven't encountered these types of words, and therefore the phonemes won't get recognized well, the words won't get written very well because the spellings may be wrong, or the specific fact that is a purchaser or seller, and this is the person who owes to that other person, those kind of relationships won't be extracted very well because it's just not enough occurrences of these types of things in the data. So the point is that enterprise data is complex and it needs domain understanding. In order to build AI models, you need to have labeled data in large quantities, and it's often very costly to label complex, and the data tends to be not very clean. It comes in many formats: text, tables, figures, PDFs, diagrams, JSON, XML files, and so on. And add to all of those format challenges and other things, there are privacy restrictions, and this data comes in many languages, languages that humans speak, and also languages with the domain specific context, like in healthcare domain and in contract understanding domain and in financial services domain and so on. So enterprise expertise is required to really label the data, and often these subject matter experts don't have that much time and they don't have enough tools to label the data, and therefore this whole life cycle of teaching AI to speak different languages becomes a very complex thing. So this is where I now summarize the first point, that in order to build an AI system that speaks the language that speaks multiple languages and that speaks the language of the enterprise, we need techniques not only to address the language of humans but also the language of the enterprise. I hope I have motivated that with those examples from healthcare domain and from contract understanding domain. But we just spoke about how teaching human language understanding itself is hard enough because of all the complexities of human language, such as idioms, the grammar that's involved in it, the cultural context, and humor, sarcasm, and all that. But then on top of it, we have to now teach the language of the enterprise. How do we make progress? So let's take a quick look. The left-hand side part of the written text is exactly the same as what you have seen before. It's doctor's notes. Now, a doctor, let's say, is taking notes, speaking into a speech-to-text system, and the system is transcribing it live because it saves the doctor time to type. So doctor spoke into such a system, and what the system has recorded on the left-hand side is what you see. The speech-to-text recognition, this particular model has been built with or trained with general purpose Wikipedia data and spoken language of general purpose domain where people are speaking to one another, or maybe newsreader has been reading and that particular newsreader's phonemes have been translated into the language model, and that's what the data that's the data that's been used to train the model. So clearly in that domain, when the base model, what I call as the model that's been trained with general purpose data, is used to transcribe or to translate from speech to text in a medical domain, it made some mistakes. You'll see instead of lower sternum, it said lower stardom. Instead of using troponin as the protein, it translated it to proponent, and acute coronary syndrome got transcribed as good con or syndrome. So that's made a mistake, and a few things like that. Now that's what happens when you take it from one language to another. In this particular case, general purpose language domain to medical language domain. However, There are ways to solve this problem without having to go get large amounts of training data to train AI models, which is what becomes prohibitively expensive and time consuming for companies to really use AI and to put it to use in different domains. But the technique here is that you don't have to solve the the entire world's all domains' problem by taking data from everything and build one model that is good at doing everything. No, you can actually take that base model that you have, which does a decent job. As you can see, it probably gets 80% of the transcriptions right. Now you say, I don't care to solve the entire speech to text for everything under the sun problem. I only care to improve it for medical domain. Specifically in this particular domain, let's say you can even go further, more specific and say for, back problem domain. And here you can customize a model by giving it more specific language that is the text related to that particular domain. And just by customizing a model with a very small amount of text data, the speech to text model actually can now fix all its mistakes because it has seen enough occurrences of phonemes, and it can now actually spell the word properly from by putting the phoneme sounds together to the word that it now knows and understands. And so what you have done on this, and you can see all the mistakes that were in red, stardom now got corrected to sternum, proponent now got corrected to troponin, good con R syndrome got corrected to acute coronary syndrome, whatever was the mistake with the ulcerative colitis got corrected. So with a small amount of data, you can correct this problem. So the insight here is that when we actually did this experiment, we figured that you don't have to solve the broad AI problem. It's okay to solve a narrow problem. On top of a decent, good enough base model, you can train with small amounts of domain-specific data to get what you want. And on top of it, further, if you want it very specific, go to individual companies' use case, customize it with that data. What that tells you is that if you look at the learning curves on the left-hand side, typically, the more training data, labeled data you give, the better the precision, which is one of the accuracy metrics is. And that's how the typical learning curve looks. The more data you give, the better it is. And of course, at some point, it starts to flatten out at very large amounts of training data. Whereas you can ride different learning curves by changing the nature of the problem. You're not necessarily trying to solve this problem. You can solve a much narrower problem, and you can get to higher accuracy as opposed to being here. You can be here just with the same amount of data, and so on. So that is a key insight that there's no shame in trying to shoot for. You can build, if you have 5 different use cases, you can build 5 different AI models for each one of those use cases. If creating one AI model that addresses all of those AI problems is turning out to be very complex and requires too much data that you don't have the time or the budget for, then it's fine. Just solve the individual problems and make progress with it. And at some point, we can come back to addressing the broader AI problem when we have more advanced techniques for taking all of the different industry context and multiple languages into account. All right, so now how do we approach that behind the scenes? What are the various techniques to solve and teach AI different languages? There are many different techniques. I've listed, roughly speaking, out of that, categorically, if you're speaking, putting all of those techniques into different groups, I would say there is a statistical natural language processing technique, there is a rule-based NLP technique category, and then there is human in the loop, which is rule learning approach. Let me take you through each one of these things very quickly. Statistical NLP is where basically what we just saw, you take a lot of labeled data and you teach the system with that labeled data to make predictions, classifications, and it learns those patterns from that labeled data, and the model is built, and now you can start to use that in production. So conventional approaches for language enablement has been that for each language, you take labeled data and you build a model and you deploy that for that particular language-based application. So you take English data, train an English model, say speech-to-text model, and you have an English speech-to-text application into which you use it. If you are enabling it for 15 other languages, for each language you take that corresponding data, you train a corresponding model, and then you have another one. The problem is that you have a separate pipeline for each language and separate application for each language, and it's very cumbersome to maintain and to host all of these different language models, and then recognize the language and to redirect it to the corresponding language model, and to manage and maintain all of these things. It costs a lot of infrastructure. It costs a lot of maintenance across all of these pipelines. But the good news is that the industry has already evolved to a better model. There are universal natural language understanding pre-trained models, such as the BERT, which is just only one of the ones. There are several others, such as that, fast text being other. There are so these are basically pre-trained language models on large amounts of multi-purpose, multilingual data. So Wikipedia data, take it in English and the corresponding translation of it in German and in Chinese and in Spanish and Brazilian Portuguese and so on. And you take all of that data and learn the correspondences between different languages behind the scenes uses a large compute to train the models, but they're pre-trained. So now you can use that. You can still have language data for each language, but you don't have to maintain the individual pipelines. This multilingual data, you can feed in all of that data, and one universal language model is learned, and you have one application cross-lingual. Already many companies who are providing AI services in different languages are already using this, and many companies are actively leveraging this to reduce the complexity of maintaining different languages. Now, you can either do this with individual general purpose data, similar to how we talked about to solve the broad AI, or you can actually start to take the top layers and customize it with the specific language or domain data to get better results. And what that would result in is that you can actually take individual industries, say insurance domain data in English, German, Chinese, whatever languages, and on top of these general purpose pre-trained natural language models, you can also start to build industry-specific context. So there is German language model that understands, let's say, a doctor who speaks into that speech-to-text system in Germany. Not only that, let's say an insurance domain, specific terminology related to that in German language will be learned on top of it. Now you can even go further and customize it to say a particular company in that particular insurance industry in that particular language, you want to customize it, and that can be done as well. So the point is that with universal semantic understanding of these natural languages, with these models that are about pretty much very much actively already being used, we are able to simplify our pipelines for training AI. And here is one example where we have trained a sentiment prediction model. We took data from 8 different languages, and we are trying to predict positive, negative, or neutral sentiment in a piece of text. Use these BERT multilingual models. If we just took each one of these English, Japanese, Spanish as 3 examples, for example, the first column indicates if we trained the models individually without using BERT, the universal language understanding model, let's say, we get certain accuracy. So this is English model trained with English data. This is Japanese model trained with Japanese data. And this is Spanish model trained with Spanish data. Now, this third column here is about using BERT, and on top of BERT, which is the general purpose trained model across 104 languages, then we add this English data on top layer and retrain it, and we're starting to see slightly better results as compared to training individual ones. So what this shows is that we can actually use these general purpose language models, and by further customizing it at the top levels with more language specific data, we can even get better results. We even went further to see, hey, if I didn't have any training data whatsoever in a language, could I still use these universal language models like BERT? Let's say here we tried it on French. We didn't have any labeled data for French at all for sentiment prediction. So we just took BERT and put it to use and say, hey, can you predict as sentiment, positive, negative, neutral? And it was doing not badly, actually, 57.96% accuracy. But now on top of it, if we actually give it some labeled data in French, it actually does even better, 64%. So this seems to be working overall. So right, so why can't we just always use statistical NLP? Well, the problem is that we had to supply, in the previous example, 100K labeled data in each language to get to that level of accuracy. And that's just actually a small amount. In order to really get to the better accuracy beyond 60%, 70%, you have to have very large amounts of labeled data. And the same goes for speech to text recognition, that the same goes for understanding entities and other things. So the foundational AI services that you need to build your business cases, such as a chat bot or a social media monitoring service, all of those require large amounts of labeled data, and it's kind of impractical to have that much labeled data in many companies. And another problem is that the system automatically learns those rules, so there's not much transparency. So if you ask it, why is this particular why did you get this meloxicam or this particular troponin word wrong, it may not be able to really backtrack and show you or explain to you that it didn't do well because it didn't have training exposure in that particular setting context for that word or anything like that. There's not much transparency, not much explainability. So there are multiple problems with using statistical NLP alone. It's good for situations where you can actually obtain that level of data, labeled data, but otherwise it's difficult. So then there are rule-based approaches, another technique, right? So if you can't get labeled data, you get people to write rules for you, because in the end what machine learning algorithms and statistical NLP is doing is really by taking large amounts of labeled data, learning patterns behind the scenes. Sometimes it might be just as easy to just let a human write a rule, and you just put that rule to use next time you see a similar pattern. And rule-based systems are AI too, and they get the job done, right? So here, for the contract understanding domain, which I have shown, let's say maybe on the doctor's notes thing, we can get enough labeled data and train a speech to text model and improve it. But where there are corporate contracts types of things that are involved, it may be much harder to go to public domain to get enough labeled data. So you have to really rely within a company, and within a company, how much data is there, contract data, and how expensive will it be to get it labeled. All of those are challenges. So what do? You ask people to write rules. So write rules, but you have to have certain vocabulary to write rules. And the vocabulary in NLP is the following, right? These are tokens, part of speech, lemmas, stop words, and you have grammar, such as verbs, nouns, adverbs, adjectives, and so on. So you understand the noun phrases, named entities, and those sort of things, and you expose that language to a user and say, hey, can you actually create a rule by using this? So for example, if you have a sentence like, John has hastily ordered a dozen dandelions for Mary from Amazon's flower shop. John is the orderer, hastily is the manner in which he ordered it, ordered is the actual order, it's the verb. What has been ordered? The dozen dandelions. Who is the benefactor? Mary. And what is the source? Where from? It's Amazon's flower shop. So if you have these vocabulary, such as who, did, what, to whom, when, you can have a user write rules for it. There is multilingual aspects even here too. So here is another example. WhatsApp was bought by Facebook, and then in different language, different, whether the subject versus object versus the predicate, the order in which they appear will change, and still the system is supposed to, in the end, from all these three different sentences, arrive at the exact same grammatical structure, that the verb is the buyer is Facebook, and the thing that's being bought is WhatsApp, right? Many Proposition banks are available in different languages, and these are being used in natural language processing for processing this translingual, multilingual data and through information extraction. So the typical in a rule-based system, what you would do is you take text like this, and using those examples, you would provide some vocabulary to users using which they may write SQL-like rules in for text. And once that rule is written, when an input such as the one on the left-hand side top corner here is supplied, the system will annotate it and will be able to extract specific verbs, nouns, and adjectives, and those sort of things here. What's wrong? And then you can, of course, expose it to the users to give them systems to correct if the system made mistakes. What's wrong with rule-based NLP? There is nothing wrong as such. Again, in certain domains, it's very useful. It's very useful specifically when you have when you cannot get large amounts of data, labeled data, and subject matter experts can write those rules, and it's much simpler for you to just capture a rule that way instead of trying to ask for lots of data to learn that rule. But you have to expose that rule, language, grammar, execution, and run times associated with those rules, and manage all of that. SMEs do not, subject matter experts, that is, they don't tend to be data scientists, and they need a lot of tools to write instead of that complex vocabulary and grammar. Now you're asking them to learn a new language to help AI learn better recognition of those different languages. But the good thing is they tend to be very transparent and explainable. But writing many rules can be cumbersome. So there are pros and cons to both statistical NLP and rule-based NLP. So there is then why don't we actually take a hybrid approach to both? Is an idea where you basically take examples, ask users to annotate on a small set, learn rules from it, and expose those rules to the users, and ask them to correct those rules if the system got it wrong. And the good thing with this approach is that you are putting machine learning to use so that you are not putting the burden to have large amounts of labeled data up front. And what you're learning is rules, which are a lot more transparent to the users. And if the rule is wrong, they can easily correct it, as opposed to a deep learning model that may have learned a pattern, but it's so hard to explain because it's learned through many levels, many layers of network, and those hypotheses are much hard to interpret and explain. So this hybrid approach of human machine co-creation of a technique seems to be working very well. And when our research teams have actually applied it in natural language understanding domain in multiple languages, when humans and deep learning algorithms worked together, we saw much better precision recall of measure scores. So let me summarize now by saying that while there are different techniques to teach AI different languages, such as statistical NLP, rule-based NLP, human in the loop, each one has its own place. Specifically, human in the loop and machine and human co-creation is good when you don't have a lot of labeled data, but you do want to have enough transparency and explainability to the users, right? So, but it does require good tools to make it easy to refine those rules, and you don't put the burden on user. So if I summarize, all three techniques are applicable. They can be used depending on the nature of the problem, the amount of data that's available, amount of labeled data that's available, and whether or not subject matter experts are willing to write rules, and what kind of tools are exposed to them to write those rules versus using both small amounts of labeled data and getting humans to then correct the rules, learning rules from the data and getting humans to correct the rules. So to summarize, I would say to teach AI multiple languages, first of all, you need to teach it to speak the language of the humans as well as the language of the enterprises. This is to put AI to use in enterprise use cases. And you don't have to solve the language of the humans to perfection to begin to address the language of the enterprise. Of course, you can always start with smaller problems and build multiple AI models. And finally, depending on the availability of the labeled data and transparency and explainability requirements, different techniques may apply, and you can choose those different techniques based on your needs and data availability and the budgets and those sort of things. So let me conclude at this point. Here are some few pointers. I am happy to take any questions at this point.
Thank you, Rama. A really interesting talk. I think one of the things that stands out is that there's been so much progress in natural language processing. Do you think we're getting to a point where we will see huge jumps in improvement, or should we be setting expectations that these are the numbers and we're not going to do a whole lot better?
Oh, they are getting better every month. In fact, the space is so fast moving. They're getting better on two dimensions. One is the more data that you are able to throw at it by collecting it from general purpose domains and special purpose domains, the better the models that exist, the techniques that exist. And the more compute you give it, the more data you can throw at it and let it learn. These are the pre-trained models, like the BERT fast text ones that I'm talking about. But also the techniques themselves are improving every day. With the GPT types of models and high compute that's available and new techniques that are being brought. So both on the algorithms dimension and the three algorithms are improving. The compute itself is becoming more and more available, and we're able to throw more compute at it, at the problem, and more data is being made available to it from general purpose domains like social media, Wikipedia type of data to train the models, pre-train the models to solve the problems. So they're getting better month by month, actually. And if you built one in 1 year, that model, you can pretty much be guaranteed that is reasonably outdated, and you would be much better off if you refresh the model with the latest.
That's a good point. Yeah. It makes a lot of sense that in a couple of years, the language has changed, and now you have to refresh. Okay, because you mentioned the data, and that there's, we have data that comes from humans, but then also there can be machine-generated data. Does that influence how you would teach your AI multiple languages?
Yeah, that's a good point. So machine-generated data adds a whole different dimension to it. It can be structured and unstructured, things such as logs, for example, that machines write, can be analyzed for different kinds of anomalies, and you can detect whether applications are working as they were designed or not, and so on. And that combination of semi-structured and unstructured data in logs poses a whole different dimension of complexity. The formats which can come in XML, JSONs, and all of those kinds of formats, you have to be able to deal with and process them differently. And there will be, messages that tell you that a system, is running out of memory, but then, there will be structured data in it, such as this IP address, this host name is the system that's exhibiting that problem. So being able to process all of that information and know which one is which requires a lot of entity recognition and also processing of the formats and such. So each one provides its own different interesting challenges. So what I didn't realize there was that glare. That's why I mentioned that it's important to then solve the problem that's at hand by really looking at it and take one problem at a time and build an AI model for it. There is no shame for that, because otherwise it's just you're trying to solve too many things and you need too much data, and in the end the model is not good for anything. So taking one problem at a time and creating special purpose AI models seems to be a very practical way to make progress these days.
It feels like machine-generated data would be very useful in fixing biases at places where we have male or female things. It's like a woman being associated with being a CEO may not happen as much in real text, but the truth is, as time goes on, Have you used machine generated data that way?
So typically, when we talk about machine generated data, it comes in a couple of formats, right? One is various devices, systems, applications. They are generating data corresponding to their health. Everything is doing well, not so well, and so on. But then at the business level, the kind of examples that you're talking about, where there may be bias and those sort of things, it's not so much system generated data. If there aren't enough, say, female CEOs as compared to male CEOs, which is the case. There's human simulating that data will only go so far, and it won't really be reflective of real world data. So I would say, in the machine generated data, there is another kind of data which is human observed machine recorded data. So this is like the surveillance data, right? Basically various video cameras that are recording on streets all the time. And you have a lot of that data that is machine data too, but it's actually machine recorded data of human actions. Humans are walking, doing things, or cars are passing by, and the system records the data. So there are different kinds of that machine data. But going back to your problem of bias, ethics, and if there are not enough data for a particular label, what do you do with it? Machine data is not going to solve that problem. That problem is to do with, there isn't enough of that kind of data in the system. So you have to really build the systems very carefully with it by either balancing, trying to do the best you can by getting enough of enough data for each label, like say for male and female, or it could be for race, ethnicity, right? Any number of those dimensions where you may not have same amount of data. You have to take extra caution in how you build those models, and how the label distribution of the training data that's going into it is. And that's really the only way you can solve it. Simulating or doing any kind of other synthetic data generation type of techniques won't necessarily be fully representative of real world. That's the problem, because you're still either learning from the small amount of data that you have, and you're either oversampling, undersampling, and they'll only go so far. If the real world itself is biased, you can ask a lot of questions on, do you expect AI to be totally unbiased in such a case? And if that is the case, how do you measure the bias or unfair bias in such a situation? And how do you test and ensure and certify that it's unbiased? And who does that? There are so many of those kind of questions. We can take that as a full track by itself, but you're starting to raise very important questions in that dimension.
Thank you so much for speaking. You can't see the comments, but everybody was just saying what a great overview this was, and so thank you for doing this. I hope you can come visit us in Houston soon.
Yeah, that would have been nice at some point when
I'll find another reason to invite you. Don't worry.
Thank you, Angela. It's been a pleasure talking to you all, and as I said, look forward to future opportunities to collaborate and interact.
Well, we will see you at the next session. Thank you very much.